Hello guys, and welcome to another calculus video. In this video we're going to be taking on a very cool looking integral. As you can see on the screen here, we're integrating from negative to infinity sine of pi x over x cubed plus 1. And as you guys can probably already tell, if you're experienced integrators like me, is that this is going to be a classic hardcore contour integration problem. One of my favorite types of integrals to take on because contour integration is just such a fun and powerful method. So without any further ado, let's jump right into the problem. So first let's do some analysis. We're integrating this function sine of pi x over x cubed plus 1. And at first we have to notice the zeros. Now there is one glaring problem with this integral, and that's that there's a pole on the real number line, because this has a 0 at x cubed plus 1 equals 0, x equals negative 1. But luckily on the top we also have a first order 0 at x equals negative 1 due to the sine function being there. So we're all good, and that's going to be a removable singularity. And the other poles that we're going to have in our complex plane are going to be at positive e to the I pi over 3, or e to the pi I over 3, and e to the negative pi I over 3 right here, and we have our removable singularity right here. Here's our origin. So we're all set to set up a nice little contour integral. So obviously we can't really deal easily with sine here, so we're going to say sine pi x equals the imaginary part of e to the I pi z, and I should put x here, right? And so we're just going to instead calculate the integral of e to the I pi x. So our contour integral is going to be contour integral of e to the I pi z over z cubed plus 1 dz. And we're going to be integrating over this path right here. We start at 0, we go around here in this direction, we take this big arc up here, and then we end up right here. However, there is one issue that we have right here, and that's this singularity right at z equals negative 1. And that's because when we converted this to e to the I pi z rather than sine of pi z, we now have a real part as well, which is that cosine part. And that real part is not equal to 0 when we are at z equals negative 1. So this actually does become a pole, just like these other poles. So we're going to have to actually take a little detour around right here. And then we're going to have to keep this residue into account. So this integral is going to be equal to the integral from negative infinity to infinity of e to the I pi x over x cubed plus 1 dx. And we'll just call this I. At the end, when we solve for I, we're just going to be taking the imaginary part. So we'll just call this I right here, and then we'll just take the imaginary part at the end, right? So we have I, and we have two other integrals that we have to worry about. That's this large integral right here, the circular arc, which we're going to call gamma, uppercase gamma, and this small arc right here, which we're going to call lowercase gamma. Now luckily the uppercase gamma is really easy to deal with, because this uppercase gamma integral is bounded using Jordan's lemma by pi over pi, interestingly. So 1 times the maximum of the absolute value of 1 over z cubed plus 1, as z varies along the gamma curve. And it's pretty trivial to see that no matter where we are on this gamma curve, this is essentially going to be, we're taking the limit as the radius goes to infinity, of course. So this z cubed plus 1 is just going to dominate, and so this is going to entirely go to 0. So we don't have to worry about this at all, due to Jordan's handy little lemma. So we can completely erase that right now. Now, a little bit of trouble happens when we deal with this right here, this lowercase gamma, because this just doesn't go to 0 because we're dealing with a pole here. Now, again, we can't use the residue theorem since we are integrating around, not all the way. We're only going halfway. We can use a very similar identity. So the way I'm going to write this, I'm going to rewrite this right here, taking out the 0. So I'm going to write this as e to the I pi over z over z plus 1 times z squared minus z plus 1. Now I'm going to rewrite this as f of z over z plus 1. And so this f of z is entirely analytic in the neighborhood of z equals -1, so we don't need to worry about it having a pole. The pole is completely encapsulated in here. So let's go ahead and make some more space. So we have our f of z over z plus 1, and we're going to be integrating over this gamma contour, right? So let's go ahead and visualize this right here. This is our point z equals -1, and we're making a little tiny loop around it, right? And we're taking the loop as the radius of this loop, which we'll call epsilon, goes to 0. So let's go ahead and parameterize this integral. So notice that we're centered around z equals -1 or z plus 1 equals 0. And so we can go ahead and set z plus 1 equal to epsilon e to the I theta. So that will just put us on this little path of this circle right here, and we just choose our values of theta to set us on the correct leg of the path. So that's going to be theta equals pi, which is right over here, and theta equals 0, which is right over here. So as you can see, as theta goes from pi to 0, our value is going to track over like this because of the trigonometric properties of e to the I theta. So when we calculate our differential, we're going to get dz equals I epsilon e to the I theta, and we're going to get the integral from pi to 0, because as I said, theta varies from pi to 0, going in the same direction. We're going to get f of epsilon e to the I theta minus 1 over epsilon e to the I theta times I epsilon e to the I theta. Forgot this d theta right here, d theta. And voila, this is going to magically cancel out on the top and bottom. We're getting an I, negative I times the integral from 0 to pi of f of epsilon e to the I theta minus 1 d theta. And notice that f here is, as we said before, completely analytic and well behaved in the neighborhood of z equals -1, which means that we can happily just take the limit as epsilon goes to 0, and we can just go ahead and remove this completely because f won't vary wildly. It'll act very, very nicely in this neighborhood, so we just need to take f of -1. Now, as a reminder, f of -1 is going to equal e to the negative I pi times -1. This shouldn't be a negative sign. All over -1 squared minus -1 plus 1, or overall we're going to get -1 over 3, right? This is going to be a -1 on the top, and we're going to have 3 over here. So we're going to get negative I pi, because we're integrating from 0 to pi, and this is just a constant, right, times -1/3. So we're going to just get I pi over 3. Nice. So this equals our gamma integral. So now we can go ahead and set up our equation again. We have integral of f of z dz, and sorry for making two different sets of f of z here. It doesn't really matter. We just know what we're doing here. This is equal to our I integral plus our gamma integral, which is I pi over 3. This equals 2 pi I times the sum of the residues. And the only residues which are actually located within our integral is the residue at z equals e to the I pi over 3. So let's go ahead and calculate that residue. So to calculate that residue, it's pretty straightforward. We're just going to take the limit as z goes to e to the I pi over 3 of z minus e to the I pi over 3 over z cubed plus 1 times e to the I pi z. Now I'm going to go ahead and split this into two limits, since this is completely analytic and well behaved, so we don't need to really involve it in the limit here. It's just going to end up being a multiplying factor. So limit as z goes to e to the I pi over 3 of e to the I pi z times the limit as z goes to e to the I pi over 3 of this whole mess. And as you can see, this whole mess, we're going to have a 0 in the top and bottom, so let's just apply L'Hospital's rule. We're just going to get 1 over 3 z squared. So when we plug everything in, e to the I pi over 3 is going to be equal to, just using our standard identities, 1/2 plus I times square root 3 over 2. So we're going to get e to the I pi over 2 plus, actually minus, because we have double i's, so minus pi square root 3 over 2. Notice that e to the I pi over 2, that's just going to be I. So we're just going to have I times e to the negative pi squared root 3 over 2. And then we have this 1 over 3z squared times 1 over 3, and instead of z, we're going to have e to the I pi over 3, so we're going to get e to the 2i pi over 3. We can go ahead and just put this on the top here. So we're going to get I over 3 times e to the negative 2 pi I over 3. All right, nice. Now let's multiply by 2 pi I in order to apply our residue theorem. So when we multiply by 2 pi I, this is just going to become, I'm just kind of struggling here, a negative sign and minus 2 pi. And this is our 2 pi I times our residue, which we know is equal to I times plus, I guess we had, what did we have? I think we were adding I pi over 3, right? And now this is just a reminder that at the end, we're only going to take the imaginary part of I. So that means on the left side and the right side, we only need to take the imaginary part since we don't care about the real parts. Now this just gets to stay as it is, but for this part, we only need to worry about the imaginary part, which is going to be the part with sign in it. So the part with sign in it, this is going to be equal to cosine of 2 pi over 3 minus sine of 2 pi over 3. And so we're only worried about this part, that I in front of it. And so we're just going to get sine of 2 pi over 3, which is square root 3 over 2. So we can just cancel this. And we're just going to end up with a square root 3 on the bottom. Then we can just not worry about any of that. And again, because of this negative right here, we can cancel this negative right here. And then we're going to take out all the i's of everything because we know that we're only worried about the imaginary part. So we take the imaginary part on both sides and we get rid of those i's right there. So our integral is overall going to be equal to, once we solve for everything, negative pi over 3 plus pi over root 3 e to the negative pi root 3 over 2. Wow, what an absolutely majestic result to a seemingly very difficult integral, absolutely destroyed by just simple contour integration and simple theorems right there. If you want a decimal approximation, I believe this is minus 0.9277 is the decimal approximation that I have for that. I guess it's actually 9278. So I hope you guys enjoyed this awesome integral, and of course, contour integration, absolutely destroying integrals is always fun. I hope to see you in future videos, and if you want to see more content like this, please leave a like. Yeah, hope you guys enjoyed. See you next time.